Mr. Burke, I'm here to reassess Standards 9.1 and 9.2 from Chapter 9 using Problem 27 from Chapter 9. Standard 9.1 is about being able to tell the difference between the situations in which one needs to use the point particle system and the wheel system, and being able to combine and use the energy equations for both. And 9.2 is about being able to calculate the kinetic energy relative to the center of mass of the system, so that's like K rotational or K vibrational, and also being able to work with inertia. Okay, so problem 27 is about a yo-yo. The hand moves up even as the yo-yo is pulled down by gravity. So the first question asks about the increase in the transitive kinetic energy of the yo-yo. So I know that the transitive kinetic energy of the yo-yo must be 1/2 of the mass times the velocity of the center of mass squared. And I know from the energy principle that my change in the energy of my system must be equal to the work of the surroundings on the system. So because I know that K is the only type of internal energy change, or K transitive, in this point particle system, I know that delta K my change in my transitive kinetic energy must be equal to the total work of the surroundings on the system, which is F net times the change in the position of the center of mass. I calculate F net through this handy free body diagram. I know that because there's a net movement down by the yo-yo, gravitational force must be more than the tension force. And given the tension force that the hand exerts on the string that the string exerts on the yo-yo, which the hand exerts on the string, and I know I can calculate the gravitational force through the mass and gravitational constant. So with these two forces, I have F net, and I know that the center of mass moves negative 0.7 meters down. So using these two things, I can calculate the change in the kinetic transitive energy, which ultimately is 0.007 joules. Next up, I'm asked about the new speed of the yo-yo. As you can see, at first I thought this would be connected to omega and to r, but then I realized that I could still use my point particle system and not worry about omega, and instead use my knowledge of the transitive kinetic energy. So because I know that the transitive kinetic energy is 1/2 mvcm squared, and I already know what the change in the kinetic transitive energy is, I can simply isolate the velocity in my equation for my transitive kinetic energy, and set up my change in my transitive kinetic energy is equal to my final K trans minus my initial K trans, and then isolate the VCM in that final K trans, which ultimately, if you go down a bit, gives me the final velocity of my center of mass is equal to 0.9 meters per second. Okay, and next up, I was working with my point particle system for these two questions, but problem C is the first one that asks me about the extended system. It asks about the increase in my rotational kinetic energy. I know I must use the extended system for this because the rotational kinetic energy is relative to the center of mass. So for this, I can't use my point particle system, so instead I write that the change in the energy of my system is equal to the summation of all of the forces all of the individual forces over their change and their point of application. So thankfully, because I only have two forces, I know that my change in my transitive kinetic energy plus my change in my rotational kinetic energy must be equal to the tension force over the distance that's applied and the gravitational force over its point of application. Because I know these two forces and their distances of application, and I know my transitive kinetic energy from the previous problem, calculating my change in my rotational kinetic energy is quite simple, and it turns out to be 0.2068 joules. Finally, the last question asks about my new omega, which again involves the extended system. I know that because it's a uniform density disk, because of my knowledge of inertia, I know that the general formula for inertia is mr squared, but for a disk, that formula is the inertia of a disk is 1/2 mr squared. So because I know that delta K rotational is equal to the change in the inertia times omega. I know that the inertia doesn't change as the mass and the radius of the yo-yo don't change in this problem. I know that my change in my rotational kinetic energy must be equal to my change in omega times my inertia. And as my change in omega is as my final omega is equal to my initial omega plus my change in omega, I can find that change in omega using what I know and add it to my initial omega and get my final answer of my final omega is equal to 41,484 radians per second, which is quite large, but then again, yo-yos do move pretty fast, so I accepted it. Anyway, thank you for listening. Have a good evening.